My friend actually got asked this question during a quant interview like 5 years ago, and I want to solve it in a couple different ways. So you repeatedly pick numbers between 0 and 1, and you stop as soon as the sum is at least 1. And the question is like, how many rounds can you expect to go?
The game might end in just 2 rounds, but you might get lucky and the numbers are small and you go, I don't know, 10 rounds. What do you think is going to happen on average? Think about it. Pause the video.
Now I coded this up, and you can look at the code, pause if you want. Here, I'll get out of the way. This helps us collect some data to see what we're looking for. So for instance, I played the game 10 times, and it looks like we always lasted 2 or 3 rounds, and on average we lasted about 2.5 rounds. Then I went and I ran it again, and I think I did 100 or 1,000 trials, and you can see sometimes we went as long as like 7 rounds, but on average we were approaching this number 2.76 rounds. It seems like we're zeroing in on something, but what is that number? How could we figure it out exactly? This is where the mathematics comes in. So when would the game end in exactly 2 rounds? This seems like a good place to start. Well, if we pick two numbers x and y, and then the game stops, that means that their sum has to be at least 1. Now, if we think about x and y as representing the x and y coordinates in the plane, then the condition that x plus y is greater than or equal to 1, that precisely means that those numbers have to land in this part of the shape, right? I just drew this graph of the line x plus y equals 1, and we can see that that happens exactly half of the time. So that means we're going to end in 2 rounds only, exactly 50% of the time. When would the game last for exactly 3 rounds? Well, our first two numbers, x and y, would have to end up in this region here, where their sum wasn't big enough. But then, when we get our third number, that must put us over the edge. And so we have to think in 3 dimensions, and so what we want to do is see where that cutoff point is, where x plus y plus z is actually equal to 1. Now it's hard to draw in 3 dimensions, and I'm not the best at it, but if you work out the region that you want, which is going to be above that triangular shaped plane, but below the kind of rest of that prism, you're going to work out the volume of that, and that would give you the probability that the game lasted exactly 3 rounds. This wedge is going to have volume 1/2, and then when we subtract off the volume of this pyramid, which is 1/6, we wind up with 1/3 as the probability that the game lasts 3 rounds. To find the expected number of rounds, we want to think that half the time we're going to get 2 rounds, and 1/3 of the time we're going to get 3 rounds. And when we multiply those things together and add, the sum of this rightmost column is going to be our expected value. So now we have to figure out the remaining numbers, and I'll tell you the pattern is not all ones. In fact, if you want to see what the pattern is, it's actually helpful to kind of recalculate the previous example in a different way. Remember, we got a probability of lasting 3 rounds of exactly 1/3, and we did that by calculating a volume. Now, if you've taken some calculus, one way to calculate volumes is by setting it up as a triple integral. Now, if you carry everything out, you see that the answer is 1/3, but this shows you how we're going to generalize instead of 3 rounds to 4 or even more than that. This is what the integral would look like for lasting exactly 4 rounds, and if we go to 5 rounds and we calculate that integral, we get these numbers 1/8 and 1/30, what we're going to add to our table. If those numbers on the left don't look familiar, I don't blame you. It's hard to see what the pattern is. But I bet you might notice a pattern on the right. After we multiply these numbers by the number of rounds, we get what I think are some familiar numbers here. If you notice, the denominators are exactly the factorials. If you look at what's happening to the denominators in this rightmost column, each time they're getting multiplied by a bigger and bigger number. This allows us to predict the pattern. Remember that we wanted to add all of these numbers in this column together to get our expected value, and so now we see what the answer is. So our expected number of rounds is just going to be the sum of all those numbers, and if I rewrite this in a slightly different way, it's the sum of 1 over n factorial as n goes through all the numbers starting with 0. Now, if you've taken calculus 2, you might know that this is exactly the number e to the 1, because you probably know this Taylor series that says for any number x you want, if you want to calculate e to the x, we'll just calculate this sum here. And that is the answer to our question. And so that 2.7 number that we saw experimentally with our code, it's actually getting closer and closer to the number e as we do more and more trials.